Over the course of this semester, we explored some basic concepts in chemistry. Chemistry is important for a wide range of careers, so if you are considering a career in medicine or dentistry, nursing, pharmacy, biology, ecology, forensics, and many other fields, you will be taking more advanced chemistry courses in the future. Before we end the class, let's briefly look at the various fields of modern chemistry that you may venture into in the future. The foundation for all other chemistry courses at any college is general chemistry. In our class, we explored some of the topics it covers. The full two-semester general chemistry sequence discusses chemical elements, chemical compounds, and chemical reactions in more detail. For instance, it introduces the special rules for writing the electron configurations of d-block elements, additional rules for writing Lewis dot structures, and discusses the flow of energy in chemical reactions. General chemistry also discusses topics not covered in this class. For instance, the properties of matter in different aggregate states, most notably the properties of gases and solutions. Furthermore, general chemistry courses usually introduce some concepts that are explored in detail in more advanced courses: organic and inorganic chemistry, electrochemistry, nuclear chemistry, etc. Beyond general chemistry, one may want to delve deeper into the properties of specific classes of chemical compounds and study chemical reactions that are associated with them. Organic chemistry deals with compounds that contain carbon. As you may remember from this class, carbon is an element that has a huge number of allotropic forms, over 500 are known today. A carbon atom has 4 valence electrons, so it can form many combinations of single, double, triple, as well as more complex types of bonds with other atoms, either with other carbon atoms, hence the variety of allotropic forms, or also with atoms of other elements, enabling an even greater variety of chemical compounds. For reasons beyond what we discussed in this class, other elements with 4 valence electrons, such as silicon and germanium, do not form as many chemical compounds. Carbon-based chemical compounds, also known as organic compounds, are ubiquitous and extremely important. Plastics, natural and artificial fibers used to make textiles, fossil fuels such as natural gas, oil and coal, food products, and so on largely consist of organic compounds. We have encountered a number of simple organic compounds such as methane, benzene, carbonic, and acetic acids in this class. Organic chemistry studies the laws that govern bonding between atoms in organic compounds and the types of chemical reactions that such compounds can undergo. Study in organic chemistry is usually required for careers in the health, food, and energy industries, in forensics, and in many other fields. Inorganic chemistry deals with all compounds that do not contain carbon. Much of the Earth is made up of such compounds. Inorganic compounds include naturally occurring minerals such as quartz, silicon dioxide that makes up much of the world's sand and that is used in the production of glass. They include various ceramics that can be used for anything from knife blades to tooth fillings to bulletproof vests. Most semiconductors that are used in modern electronics are also inorganic materials, as are many dyes and paints, although organic materials can also be used in both of these applications. Of course, water, probably the most important compound for life on Earth, is also an inorganic compound. Its molecules consist of 2 hydrogen atoms and 1 oxygen atom, and do not contain carbon. Inorganic chemistry studies the laws that govern bonding between atoms in inorganic compounds and the types of chemical reactions that such compounds can undergo. Studying inorganic chemistry is required for careers in various branches of the chemical industry, including the production of catalysts and fertilizers, metallurgy, semiconductor processing, etc. Organic and inorganic chemistry sometimes overlap. For instance, in organometallic chemistry that studies compounds where carbon atoms are bound to metal atoms. Furthermore, many reactions in organic chemistry require inorganic catalysts. Biochemistry is the study of chemical processes in living organisms. Such processes often involve both inorganic and organic compounds. Biochemists study some of the most complex molecules that are essential to human, animal, and plant life, including proteins and DNA. Such molecules are made up of thousands or even millions of atoms. Modern biology relies heavily on biochemical methods, so understanding biochemistry is essential for doctors, pharmacists, and other health professionals. Analytical chemistry studies the methods that allow us to determine what elements and/or compounds a sample of a given substance, whether a chemical compound or a mixture, consists of. The two branches of analytical chemistry are qualitative and quantitative analysis. Methods of qualitative analysis allow identifying what components are present in a sample, whereas methods of quantitative analysis allow identifying how much of each component is present. Analytical chemistry courses discuss methods and instruments that are important across other fields of chemistry, as we often need to figure out the composition of both organic and inorganic compounds, as well as of their mixtures. We have used some basic analytical chemistry techniques such as filtering in the lab associated with this class. Studying analytical chemistry is required for careers in forensics, environmental sciences, and materials science. Physical chemistry explores the underlying principles of chemical bonding. Students occasionally call it general chemistry on steroids. Physical chemistry uses the principles of quantum mechanics to describe atomic orbitals, calculate their shapes and sizes, and see how they change when atoms interact with each other. It allows discovering rules that explain why atoms of chemical elements bond with each other in specific ways. Physical chemistry also uses the principles of thermodynamics and kinetic theory to explain why certain reactions occur very quickly, other reactions occur slowly, and some don't occur at all, as well as why some reactions require heating and others require light or a catalyst, etc. Learning physical chemistry helps better understand the rules of chemical reactivity that are studied in organic and inorganic chemistry, as well as the principles that underlie the operation of chemical instruments. Studying physical chemistry requires a foundation in physics and math, so 2 or 3 semesters of physics and calculus are usually prerequisites for physical chemistry courses. In addition to the fundamental subfields of organic and inorganic chemistry, biochemistry, analytical and physical chemistry, there are also multiple applied subfields of chemistry. For instance, forensic chemistry studies chemical methods that are applied to evidence in investigations by law enforcement. Environmental chemistry studies chemical processes that are relevant to environmental science. Pharmaceutical chemistry studies compounds that can be used to treat medical conditions. These and other fields of applied chemistry draw on organic, inorganic, and analytical chemistry, as well as biochemistry to solve problems of practical importance. Computational chemistry uses the principles of physical chemistry to simulate the properties of chemical compounds and chemical reactions on computers. Insights that such simulations provide can be useful in both fundamental and applied subfields of chemistry. Chemical engineering studies processes that are used for large-scale industrial production in the chemical industry. Modern chemistry is truly the central science. It is closely related to physics, biology, environmental, and health sciences. And chemists all over the world work together with other scientists to make our lives better. This class was your first step on the journey towards understanding chemistry. I hope you enjoyed it.